We're all kind of drowning in data these days. From financial markets to climate science, the sheer amount of information we have is just staggering. And the classic tools we've been using to make sense of it all, they're getting overwhelmed. It's like trying to navigate a whole new continent with a really old, really outdated map. So today, we're going to look at some groundbreaking research that's drawing the new maps we so desperately need.
So let me ask you a question. At first glance, what in the world could connect the chaos of the stock market, the massive complexity of climate science, and the super detailed data from a single patient in a hospital? They seem like they're from completely different universes, right? Well, it turns out they all share one fundamental, very modern challenge. And that challenge is this: a total flood of data that isn't just big, it's incredibly complex. We're talking about high-dimensional data. That means thousands, sometimes millions of variables all at once, and it's interconnected, where everything can influence everything else over time. This is exactly where our old maps start to fall apart. Okay, so to really get why this is such a big deal, we first need to appreciate the tool that's been the absolute cornerstone of statistics for centuries. It's called the central limit theorem, and for a very long time, it was the most reliable, most trusted map any data explorer could ever ask for. The idea behind the classic CLT is actually beautifully simple. It says that if you take a whole bunch of random, independent variables, and that word independent, I can't stress this enough, is the absolute key to the whole thing, and you average them out, the distribution of those averages will almost always form a perfect, predictable bell curve. The process itself is surprisingly straightforward. You just dip into your data, take a random sample, figure out its average, and put a little pin on a chart. Then you do it again, and again, and again, thousands of times, and after a while, something incredible starts to happen. A beautiful, predictable pattern emerges from all that chaos. And here it is. This is the magic. Look at how most of those sample averages are clustered right there in the middle, around the true average, and they get rarer and rarer the further out you go. Even if the original data was a total mess, the averages create this gorgeous, orderly shape. This turns randomness into something predictable. It's what made the theorem so powerful for so long. But there's a catch. And the catch is that this classic theorem, this beautiful old map, was built for a world that's, well, it's rapidly disappearing. The new world of data is this wild, uncharted territory where the old map doesn't just fail you, it can be dangerously misleading. In fact, don't just take my word for it. The researchers behind this new theorem, they don't mince words. They literally call the search for new methods an urgent demand. So this isn't some quiet academic exercise. It's a direct response to a very real, very pressing crisis in the world of data analysis. So here's the core difference, boiled down. The old map was designed for data that was low-dimensional and independent. Think of flipping a coin. One flip has zero effect on the next. Simple. But modern data, it's high-dimensional and deeply dependent. Think about the global stock market, where a tiny ripple in one corner of the world can trigger a tidal wave that affects thousands of other stocks in seconds. They're all linked. So the crucial point is this: that fundamental assumption, the one about independence that the entire classic CLT is built on, is just flat out broken in most modern datasets. And when you try to apply that old map to this new, complex terrain, well, you get lost. You end up with flawed conclusions. And this is where our new cartographers, the researchers behind this paper, come into the story. They saw that everyone was getting lost, and they decided to do something about it. They set out to forge a totally new rulebook, a new set of maps designed for the territory we actually live in today. And let's be clear, this work isn't just some minor update or patch. No way. This is a whole new generation of central limit theorems. These researchers have basically built a comprehensive new toolbox from the ground up, specifically for that high-dimensional, dependent data that's been tripping everyone up for years. And get this, they didn't just create one new map. They created an entire atlas. Their work gives us different frameworks for different kinds of data terrains. For example, think about the weather. A huge storm today definitely impacts the forecast for tomorrow, but it has almost no effect on the weather a year from now, right? That's called amixing. Then you have something like physical dependence, where the impact of an event just kind of fades away over time, like ripples in a pond. Each one is a specialized tool for a specific kind of data landscape. Okay, this slide might look a little technical, but stick with me, because this is one of the most powerful features of their work. That dimension p, that's just the number of variables,
is allowed to grow incredibly fast compared to the sample size n. This means their theorems actually work, even in these extreme situations where you have way more variables than you have data points, which, trust me, is super common in fields like genetics and finance. It's a huge deal.
All right, so this is all really fascinating theory, but what does it actually mean in practice? Let's take a look at how this new map turns all that complex math into some really practical, really powerful applications. The real-world applications are vast. With these new tools, economists can finally test if their super complex financial models are actually, valid. Climate scientists can spot a change point. That's a sudden, critical shift in a data trend, like ocean temperatures suddenly spiking. And engineers can finally tell the difference between meaningless background static, what they call white noise, and a very faint but very important signal hidden inside of it. And ultimately, that's what it all boils down to. This research provides a solid foundation. It gives scientists, analysts, and really anyone making big decisions the confidence to know that their conclusions, drawn from all that messy, complex, real-world data, are statistically sound. It's all about replacing uncertainty with reliability. So, what does this all mean for the future? We've just seen how one of the most fundamental rules in all of statistics has been upgraded for the 21st century. And honestly, this points to a much broader trend. So, if you're going to take anything away from this, let it be these key points. 1. Modern data has simply outgrown our classic tools. 2. The central limit theorem, a true legend in statistics, has finally gotten the upgrade it desperately needed for this new reality. And 3, this work gives us a much more solid foundation for analysis, which means we can get more reliable insights in pretty much every field, from finance to biology. And that leaves us with one last fascinating thought. We just looked at the reinvention of one major statistical law. But as data keeps getting bigger, messier, and more complex, you have to wonder, what other foundational rules of science and statistics are next in line for a modern upgrade? It's a powerful reminder that in the world of data, the maps will always need redrawing.